we could. Okay, so now we have the final talk on this 3-talk series on MIP star equals ARI, and our next speaker is Professor Zhengfeng Ji from University of Technology, Sydney, who is another co-author on this paper and will wrap up this series.
Okay, thanks, Andres, for the introduction. I think I hear some echo. This is Zhengfeng Ji talking from Sydney, Australia, and first I should thank the organizers for making this happening, given the time of crisis, and also I noticed that the shift of the schedule, so that makes it easier for me for my time zone. So I will talk about MIP star equals RE, the third part of this series of talks. And that is, I want to build upon the techniques that you have seen so far in the workshop, and to give you a proof of MIP star equals RE, particularly on Anna and John's talk. So this is John work with Anna and Thomas, John and Henry. And first I'd like to give you some background just to be sure that we're on the same page. We start with MIP. You have seen this many times. I won't go into the details. And you have also seen Magic Square games. You can think of the game as, you can turn it into like to prove a game. And the thing that I want to emphasize that if you look at these games, the power of the actual prover, where the power comes from is actually because like we can interrogate these provers and do cross checks. And what means that we have a very interesting so-called question distribution. If you look from Alice's view and Bob's view, they knew partial information of other players' information, but not complete information. The questions are correlated in some way, but it's some interesting structures in there if you look at games that are interesting. So adding entanglement between the players, you have the class MIP star, and it's pioneered in the work of Cleve et al. And I think like it's beautiful because it connects multi-prover intact proofs to Bell inequalities. And also notice the soundness problem caused by entanglement, because like entangled strategies would have higher values, so previously classically sound protocols will not be sound quantally. And it also opens the door to developments and applications of quantum analogs of many powerful ideas in interactive proofs, like loadable tests, parallel partitions, and PCPs. Most of these are the techniques that we use in our work. We give some definitions of the model that we study. We call local games, and it's a very simple object. We have finite question sets X and Y, and finite answer sets A and B, and the question distribution mu on X, Y, and also a decider. So given the tuple of question and answers, we want to make sure whether we decide accept or not. And as John has been telling you, we would also consider a family of games defined by a verifier, which is a pair of Turing machines. One is called S sampler, and the other is a D decider. And so it's easy to understand the role of D. So you have an index N, and then it's the question answer tuple. And the machine sampler S, basically, it's implementing the sampling procedure, and you can think of the sampling procedure as from this random seed Z, apply some function LA and LB to get the questions for Alice and Bob. So the machine S is actually specifying the computation of LA and LB in some sense. And then when we hardwire the index N, we would get the nth game defined by the Turing machine, we call it Vn. So that's the notation that we will use in the talk. So once we have the game, we'll consider two values. One is called entangled value, and the other is called commuting operator value. And basically, a strategy, entangled strategy is a tuple of state and measurement. State is in the tensor space. And then the entangled value is you maximizing over all possible strategies of the winning probability. And that's expression for the winning probability. And what's magic for magic square is that the value is, entangled value is 1, even though that the constraint system has no classical assignment, satisfying assignment. And basically this class of MIP star is about the problem of approximating the value, entangled value of our star to some precision, given certain size. And very similarly to this definition, we also consider commuting operator strategies. The difference is now we have a single Hilbert space. There's no tensor structure, and we require that Alice operators and Bob's operators are commuting. And this gives you a definition of commuting operator value by optimizing overall strategies. And I guess you have seen this problem in William's talk. Searson's problem asks whether these two values are the same for all games. And I should mention that for finite dimensional Hilbert spaces, these two values do coincide. And so it's really a problem about what happens when space H is interdimensional. There are two algorithms that we know for these two values. The first is a triple algorithm. You just do exhaustive search for better tensor product strategies of increasing dimensions and increasing precisions. And this gives you a sequence of values that approaches the entangled value of our star. The other algorithm is very non-trivial, and basically it's a non-commutative version of sum of squares, STP hierarchy, also known in the community as NPA hierarchy, following this reference. They would give you a sequence of STPs whose value converges to the commuting operator value from above. So the first algorithm implies that the class MIP star is in RE, and a more interesting consequence is that if Searson's problem has positive answer, meaning that these two values are the same, then you have an algorithm for approximating this value because you can alternate in between algorithm 1 and algorithm 2. So that's a complexity theory consequence of Searson's problem having positive answer. But what we found out is that actually MIP star equals RE. So there's no algorithm that you can approximate the intended value because it is as hard as a Hawking problem. In some sense, this gives like a complete characterization of the class MIP star. And I guess in like following the saying of Einstein describing entanglement as spooky action at distance, we would like to call that our result is a spooky complexity at a distance. It is also interesting to think of the results from the Bell inequality perspective. We say that it's a computability theoretic Bell inequality because, like John Bell tells us that for certain games the values are different, but in our result we show
Zhengfeng, there's a bit of echo when you speak, so could you maybe like turn your volume a bit lower or move closer to the mic, or I don't know why it happens.
Yeah, okay. I'll try to turn down the volume maybe.
Okay.
Maybe I'll stay far.
This is Omid with Simon. I would recommend that maybe you just hold your microphone closer to your mouth.
Okay. Because like if you think about what John Bell is telling us is that you have certain games where the values are different, but our result says that if you look at the computability of these values, they are different. The result also have consequences in physics and mathematics. It gives an active answer to Searson's problem and gives a refutation of Compton's embedding conjecture, which is a major open problem in operator algebra. I guess you have seen a lot of discussions in William's talk. So this is a very quick introduction, and next I would review the key ideas and techniques that we rely on. Basically, you have seen most of them. maybe it's like a good point if we have questions. Let me start. The first thing that very technical thing that we rely on is the distance measures. If you look at the papers, like maybe 70–80% of the proofs are using this language. It has been around for a while, maybe 10 years now, and it evolved from paper to paper. And I recommend that you read Anna and John's paper, because it's really nice way to present what we need. And there are two distance measures that are important. One is called state-dependent distance. It's a measure between two set of measurements acting on the same space, like in this figure here. You also need a consistency measure. It measures the distance between two set of measurements that are acting on different spaces, so Alice and Bob space. And using Cauchy-Schwarz, a lot of interesting properties have been shown, and basically that's the main tool that we reason about when we massage the strategies to argue about the properties. That's the main technique that we use. And then another early technique that we rely on is trying to solving the soundness problem of entanglement, and we call this entanglement resistant techniques. So, for example, you can do a check called confusion check, and suppose that the verifier is interested in the value, the assignment to variable x, but the verifier would sample another variable y and ask Alice to give assignments to both x and y by permitting the order of x and y, that hiding which variable that the verifier is actually interested in. And doing such checks, you would be able to derive that the measurement corresponding to x and y are approximately commuting on state. Then it is like some classical condition that you can, like a situation that is similar to the classical condition. And like you can also use monarchy of entanglement, and such simple techniques would enable you to prove that entangled games are already NP-hard. These are very early investigations. And I guess in that set of techniques, what is surprising and most important to us is that like low degree tests and multilinearity tests and linearity tests are found to be quantum sound. So these are tests that are widely used in classical interactive proof systems. And you don't need to like do much of modification, and you can have the quantum soundness, meaning that having entanglements between the players, the proofers, don't help them to cheat. So the guarantees of this test are the structural results of this test, meaning you have a linear function or multilinear function behind the scene, is being preserved even you have entanglement. And I think that's the first breakthrough in this area. And the results also allowed Ito and Thomas Wittig to prove that NX is an MIP star, and that's telling us that at least the quantum class is as powerful as a classical class. So next piece of tool that we need is rigidity. You have seen in-depth discussion in Andrea's talk. And so I won't repeat what it means. Basically, we would have a way to enforce the players to measure honest measurements, X and Z's. If you look at the magic square game, it's all about commutativity and anti-commutativity. So the variables that are on the same line or column are commuting, and the variables like x1, x5, not on the same line, are anti-commuting. And anti-commutativity is really important for us because by this simple lemma, if we have like two reflections that are anti-commuting approximately, then there will be a local isomorphism so that these operators are essentially x and z. And once you have x and z, you have like two-dimensional space, and you can find a qubit. This is important because from the perspective of the verifier, you send out and receive classical informations, and only by rigidity you can argue that there's a quantum system out there. So building the upon the idea of rigidity, we can go beyond NP hardness. It's not an easy thing to do. Like it took us many years to figure it out. And I guess the interesting thing that this idea came out of discussion at Simon's Institute workshop in 2014. So thanks Simon Institute for supporting the research. The idea is that you can use quantum error correcting code to encode quantum information. For example, you have like a QMA witness state. You want to design a non-local game from that. What you can do is you can encode each qubit into using this quantum error correcting code. Like here, it's 4-qubit code, and each like you have 4 provers, and each prover would hold 1 qubit of the encoded qubit, 4 qubits. And using rigidity, we can ensure that provers measure honest X and Z measurements on these encoded states. And then we can do logical measurement, because logical measurements are, you can take parity to measure the logical operators. And then we can check the energy of the encoded state. So this is how we design protocols for verifying QMA. And another like consequence of rigidity, I think it's important for us because like it joins the forces of low degree tests, the quantum soundness of classical low degree tests, and rigidity. Basically, it's using a lot of magic squares, as you've learned from Anand's talk, and you have a powerful game that we call a Pauli basis game. Basically, what it gives you is if you send the question Pauli W, where W is either X and Y, to the players, then they have to measure the basis in X and Z and report the measurement outcome. So as you can see that in the rigidity theorem, the measurement that corresponds to this command is essentially the honest Pauli measurements. And it's also very efficient, meaning that the messages are much smaller than the number of qubits you are testing. So this gives you the ability to self-test and EPRs, and you can like to remember that you have now a primitive called Pauli W, where you can command the players to do Pauli measurement and respond with the measurement outcomes. It is important for us to understand the question distribution. Like I've been saying that it's important that the question distributions of different games are interesting. And for us, the understanding the question distribution of the Pauli basis game would help us to understand how the proof works. So remember that the question distribution are being sampled by first sampling a seed Z and then applying some functions to apply it on Z and send it to Alice and Bob. There will be different types of questions that we consider. The point questions and plain questions are for the low degree tests. So we need one for X basis and one for Z basis. The pair types questions are for testing commutativity of Pauli operators that are commuting. And the constraint variable types are for the magic square game, testing the anti-commutativity. So for example, in the point type, so basically we will have a very uniform format for the questions. They will have like this type and content format, but type is some discrete set of labels, and content is a vector in finite field F to the 4m plus 2. For example, the UX is the point for the X measurements, and UZ is the point for Z, and V1, V2 are the directional vectors defining planes in this space F to the M, and Rx, Rz are for this. Try to converting this high dimensional, as it's over field F to bits. So these are the type of questions that we need in the points. type of questions, we want to review the point of x, so ux is revealed, or other coordinates are zero out. You don't let the players to know what the seed has in these registers. So you just replace them by zero. And you can do this by the revealing and hiding technique that John has been telling you in the introspection technique. And similarly for the planes, you would first review the directions, and then depending on the direction, you partially review the point information. You don't want to give the point directly to the player, because that would violate the requirement that we want to build interesting distribution that Alice won't know Bob's question. So that's essentially what we all need for this poly basis game. And here there's the graph. It's like a type graph where what we would do, we would sample an edge and then send the type one vertex type to Alice and the other vertex type to Bob, and also apply this procedure to review and hide information. So that's how we like redefine the distribution, and you can see that it's essentially the same as the poly basis game distribution in early presentations. The next idea that we need is about compression. It is a very natural thing to consider once you have you want to prove something like MIP star equals to RE. But the idea actually appeared earlier when we want to try to improve the lower bounds. I remember that I was giving a talk at Stock and about the classical verification of QMA, and at the end of talk, Aaron Harrow asked the question whether you can go beyond of QMA and prove maybe like for example QRP is local games are QRP hard. And I said at the time that maybe we can build like more relations out of the rigidity conditions. Right at that time we have like commutativity, anti-commutativity. But if you can build more sophisticated relations, then you maybe you're able to prove more. I guess I wasn't too far off the point, because later on William found out that you can actually enforce this kind of conjugacy relations and use this to prove that the set of quantum correlations is not closed, and simplified his breakthrough proof of non-stability of the linear constraint system games. But later on, a very simple idea came to me, and it's motivated by this classical result of Marriott and Watchers. Basically, QIP is QMEM. It's not that far from QMA because it's a single extra letter, right? And if you look at the structure of this thing, it's almost like QMA, but at some certain step, you would like the prover to do a big unitary. But if you think about it, you can do propagation checking for this kind of particles. And what this will give you is a compression for MIP star. So that's how the idea came up. So the compression would give you, now you start with a big game, even though that in the paper there's a lot of players instead of two, but you end up with a game where the question sizes and running time of the verifier is much smaller. The problem though is that we have a problem with the gap. And I guess this table summarizes the situation, and it's, even though like we lose a gap, it's also interesting. Because if you write down what we have for the classical case, like MIP and the scaled down version, we have like a game for a CSP problem, for example. Then the message size is especially small, and the complexity goes down from NX to MP. And the gap for the MIP, of course, constant. The gap for the games, trivially, it's inverse polynomial, but by the PCP theorem, it can also be a constant. Now, in the case of quantum, that you have a star, when you reduce the size of messages, what this compression theorem gives us, that it doesn't go down from the MIP star to maybe especially scaled down version of MIP star, it still stays at MIP star. And that's interesting because we have seen some differences in these two setups. And the idea then is that if we can amplify the gap from this inverse polynomial to constant, then you would have something like disability of the MIP star. So what we want is to try to amplify the gap, and maybe in today's language, it's like social distancing for the completeness and the soundness. And also we know how to do gap amplification. In the classical literature. You just use PCP, and the basic idea is whether it's easy to throw in some PCPs and get better results. But that's not that easy, because if you think about all these early results, they are using this encoding using error correcting codes. And the property of error correcting code is that locally there's no information. So the proofers have like one bit of error correcting code, and the density matrix are maximally mixed, and there's no information locally. So, and all the information is actually in the parity of this player's answers. And this is not a setting that you can easily work using PCPs. So then, and you already have seen this, the next idea to solve this problem is very clever idea. Is and also gives you a different way to prove compression theorem. Is you let the players to sample the questions themselves, and that's introspection. And like to summarize what is happening in introspection is actually utilize Heisenberg uncertainty principle to design what you want to reveal and what you want to hide from the measurements of the EPR pairs. So for example, you want to implement LN and LP and use that as the question distribution. What you want the introspection to work is you want a so-called intro primitive. And once the player receives this command of intro, they have to measure the EPRs to get the question why, and it's supposedly this LV, like LV of Z, where Z is the Z measurement outcome of the EPRs. And then once you get the big question, you can measure as in the original strategy for the verifier, for the player V to get the answer A. So this is what we want to achieve. And we have seen examples that this is possible for distributions like the low degree test, the line point distribution that used in low degree test. Okay, so that's a very quick discussion of the techniques that we rely on. And so in the rest of talk, I would try to put everything together and give you a proof of our result. So in the end, we will have several different steps to do the compression. I guess from John's talk, it's very natural to have some introspection step. You want to use this idea to reduce the size of the questions, and also a PCP to reduce the size of answers. And oracleization is a pre-processing step for using PCP. And you also need parallel repetition to recover the gap, because along the way, the gap is getting worse. And that's what we found to be useful in the compression. And it's not clear that you have to go from 1 to 4. It's just some combination of the steps. But we found that this sequence would just work. And like a focus would be how to use the introspection idea that introduced in John's talk to do question reduction. And the question that we need to ask is what is missing from the protocol that given by Anna and John. So basically, they start with MIP star particle and we'll end up with a smaller particle, but the starting point has very special structures. Basically, it's the variant of nxp equals to MIP particle of BFL. But after that, it will be a much more complicated game, and you cannot like sticking in the output as an input to the procedure and get smaller and smaller compressed games. So the idea then is very natural. We want to find some so-called normal form, where you start in a game of this normal form. After the compression, it is a smaller game and is still in this form. Then we can apply this argument recursively. So there are two problems that are important. The first is that we want to understand what kind of distributions. Basically, it's, the answers and decision procedure are easy. We want to understand is the kind of distribution that we can apply this introspection technique to. It is not that all distribution that we can apply to. There's some very special family of distribution that we can apply the introspection technique. And also another question is what the output distribution would the game after the compression use. And we want to make sure that these two matches. And that would be our normal form. So I'll just give you the solution that we found. And this is called conditional linear functions. So basically, these are functions. If you remember that from the seed Z, we want to compute LA of Z and LB of Z. And these are describing the functions of LA and LB, how you compute the question from the random seed. Conditional linear functions are very simple. It's a generalization of linear functions. So basically, you would choose register subspace of f to the n. So think of this long string here as a vector of entries of elements in field F. And maybe V1 is just the first 10 elements. And if we apply a linear function to this first 10 elements, and then we have some output Y1. So Y1 is some linear combination of these first 10 entries. And the linear function may not be one-to-one, so we may lose some linear information of Z1, and that's the hiding part. And once you have seen, like learn Y1, you can condition on Y1 and do something similar to the rest of the bits. You will choose a space V2 and then apply a function, which both, like where both the subspace, where the qubits are, and what functions you use are depending on the first information Y1 you see. And you repeat this L times, and we call out the number of levels of the CL function. You can get Y1 to YL. And then the output of the function is the collection of all the yi's. So you sum over all these yi's, you get the output y. And then the linear function, conditional linear function is just from z to this y. So it's extension of linear functions with a sequence of conditioning of intermediate outputs. So why we consider such functions? Well, first of all, it's very natural to consider linear functions because they work so well with the technique of introspection. Basically, it's revealing and hiding linear information, and it works well with X and Z measurements, and as you can imagine. But linear functions are not enough for us. Even like in the classical low degree test, you want to have this plane and point distribution, especially in the plane distribution. You want to reveal the directions, and then you need to apply some function that is depending on this V1 and V2. And after that, it's linear function. But if you compute this computation from the seed to the output of the plane, it's not a linear function, but as in our definition, it will be a two-level CL function, because the first thing you reveal linear information over the direction register, and then you condition on this directions, you reveal the information about the point that you want, point information, partial information about the point you want to reveal to the plane player. So, and basically you can verify that CL functions works, and they can model all the question distribution that we want, and they have very nice closure properties. So for example, if you do pair repetition, you means CL. But for us, it's the only technical part we want to verify that poly basis game uses CL distribution. And that's easy to do. The most non-trivial part is actually this thing. And this is already been solved in Annan and Jones' paper. So the next thing we want to, so we have a definition of CL functions, and we will see that that you can actually design an introspection game for sampling these distributions. So to make things simple, we consider two levels of CL functions. So there will be R1 to H2. You first review information in R1 and hide information in H2, and then condition on what you see in R1, you decide where this R2 is, and you read the information and you hide the information in H2. What we want is then the primitive of intro for Alice, for example, and we want the player to behave in a way where they will only measure this R registers where we want to reveal information, but measure nothing, which is identity, on this hiding registers. And also, once we have this R1 and R2Z measurements, you get the information Y, which is the question, and then you should also be able to measure the answer of the input game, the game that uses this distribution, CL distribution as questions. But how do you enforce that behavior? That's another use of the idea of the data hiding technique, or the introspection technique of Anna and John. Basically, what you can do is the way you ensure that the intro won't measure H1 and H2 is that you introduce Z measurement and X measurement, and you check that no matter whether you measure Z or X, they will be all consistent with this intro type of question, and that's the data hiding technique. Because like the independence of this intro type on this information in H1 and H2 is important. We want to make sure that the answer A is only depending on Y, but not on all the information. That's important for preserving the information perspective of the players. So the rest of the construction is easy. We want to make sure that all these Z measurements are honest, and this is simple. We want to cross-check this sample by the poly Z primitive that we have from the poly basis measurement. And similarly for ensuring this X measurement, well, for some technical reasons, we've introduced multiple height types, where the number of height types is the number of levels. So let's see what we need to check. So the first, we do a cross check between intro and sample. We would maybe send intro A to Alice and intro sample A to Bob. And these colors are where we check. So the Z measurements on this register should agree, and the answer they have also should be the same. So that's from this information Z, you can compute by the conditional linear function A to get Y, and also the answers are the same. And then you check that this Z measurement in sample are honest by cross-check this with the poly type of question. Similarly, you cross-check read and intro, where read is like you not only measure the information that you need, but you would purposely erase all the information using X measurements. The trick that John has been telling you. And then you want to make sure that these X's are honest, and we do this by removing this Z to identity and check that all these remaining things consistent, and gradually we check that these axes are consistent and all these axes are consistent. So it's a chain of checks leading to this poly X to make sure that these X measurements are honest. So that gives you the structure or the definition design of the intro game that we have for a general conditional linear dispute functions when there are two levels, and you can easily extend it to L levels for any constant L. To summarize what this intro game is doing, you can think of two ways of playing a normal form game. So you have a game Vn, which is specified by Sn and Dn. In the standard way, the verifier would sample the random seed and cause Sn to compute the questions using these functions to get X and Y. And then you receive answers from Alice and Bob, and you can use the decider to determine whether accept or reject. The other way, the introspective way, is you do this introspection game. So what the verifier would do is first play the polybasis game over EPR of this particular dimension. So if the Z measurement of the EPRs would give you a Z in this space, F to the N, F to the N. And then we run the remaining parts of the intro game. So intro game is using the polybasis game as a subgame. So the remaining part of the game, and that part is what we introduced in tables. And it ensures that players to respect the intro primitive. And lastly, you just send intro to Alice and intro B to Bob, and then receive X and A and Y and B. Because if you trust that this all works, the players has to sample the large question and get do this measurement to get the large answer and or report back. Then you can use the decider D to test whether accept or reject. And so that's if you look at the question size of the polybasis game and the introspection game, it's much smaller than the standard way of playing games, where you need to send all this F to the N amount of information. And that's how we reduce the question using introspection. So if you look at the question distribution, we know that maintaining the structure of question distribution is important, because we want to make sure that in the end it's still good manageable distribution. And if you look at all this new type of, we have this polybasis types from the polybasis game, which is complicated. But for this new types, they would only consist of the type, and there will be no information needed from the vectors. It will all be 0. That's because the way the game is designed, and then you can see that for each type, for each given type, the information you have can be computed from the seed using a CL function. And then the next thing is that you want to get rid of these types. So the types are forming arbitrary combinatorial graph. You want to simulate this distribution defined by the graph using conditional linear distributions. And that's possible with especially going overhead, but that's okay, because we only consider finite size type graphs. And another thing that was mentioned is we only need constant levels of conditioning. So in the end, we will consider 8-level CL functions. We start with 8-level CL functions, do this compression procedure, and we get 8-level CL distribution as the outcome. So that's how the introspection works. Then in the next several steps, I'll quickly remind you what they are. And first you do oracleization. And this is because we want to apply the PCP technique. And basically we want one prover to have every all the information. So all the questions X and Y and A and B are at one prover side. So, and for this to work, we want to require that for the perfect strategy that we consider in the completeness condition, all the measurements that Edison Bob uses are always commuting. Well, they are commuting because they are acting on different hyperspaces. We want they to be commuting even like we moved Bob's operator to Alice. So when they are operators acting on the same space. And that's the reason that we actually required multiple high types in the intro game. Remember this table here. Like we want to ensure that X's are honest. Why don't we just cross-check read and party X? Well, that will introduce the measurement where the measurement on Alice's side measures Z and on Bob's side measures X. And that's not commuting. But like introducing multiple high types, you can avoid this problem. So every time you measure any measurements on Alice and Bob's side, they are always commuting in the sense that they are commuting on the same space. Okay. So the next step, you want to use PCPs and parallel partitions. And we won't spend much time talking about it because basically it's very similar to what Anna and John was doing in their paper. What we want to make sure is that this transformation won't break the condition that the distribution is CL. And there's some variations that we did to make this easy to prove. And then after that, you have like a game where both the questions and answers are small now, but the gap is getting worse. So we apply parallel partition, and in particular, we use the anchored parallel partition to, for some technical reasons, basically we want to have the best entanglement bound that we can have. And then like combining all the steps, you will have a gap preserving compression of normal form games. You start with a game using CL, 8-level CL functions. You end up with a game with 8-level CL function, but it's much smaller size. So okay, now you have a compression theorem, and so it's stated like this. It's an algorithm with input V and output V sharp. So both V and V sharp are a pair of Turing machines. And the conditions we have is that this compressed games, they are on a much smaller index, but they can simulate the larger game in the sense that if the larger game has value 1, then the small game has value 1. If the large game has value at most half, then the compressed game has value at most half. And also we have interesting entanglement bounds that the compressed game would use at least that amount of information in the uncompressed game, entanglement in the uncompressed game, and some fixed bound because of the use of entanglement in the introspection. So that's the technical theorem that we want. And once you have that, what you can do now is to define a Turing machine. So we were trying to prove that MIP star equals to RE, and basically we want to reduce the halting problem to deciding the value of a game. And this is how we do it. So for any Turing machine M, we define a Turing machine called D hot, the decider for the hot game. First, you will simulate the game M for n steps, where n is the index. It's the input of this decider. If M already hots in this n steps, we accept. Otherwise, we don't know. Then we just compress the decider itself to get the compressed decider, and we only accept if the compressed decider would accept. So intuitively, because the compression theorem guarantees us that the compressed game of index n is simulating what this uncompressed game d hot over 2 to the n index. So it's essentially checking in this step, like to simulate m for 2 to the n steps, and if it halts and accepts. So as you can see, like if m halts eventually, then the game should be able to detect this. So the Kleen's recursion theorem is used here because like we are defining a Turing machine. While specifying the Turing machine, we use its description, and that's well, it's maybe counterintuitive, but that's allowed by the Kleen's recursion theorem. So that's machine, the Turing machine d hot is well defined. And based on this definition, we can claim that if m hots, then the entangled value of this game of particular size n0, where n0 is where the compression works. Compression theorem works for n at least some fixed constant n0. And the way to see this, like if this Turing machine halts in t steps, and if like t is less than n, then you would already see this in this first step, and of course the value is 1. But if like, for example, it's in between n and 2 to the n, then by this simple argument, the value of this in hot, v hot on index n, because it's t is larger than n, it doesn't really hot except in the first step. So we move on to the second step, and we'll only decide accept if d sharp accept. So it's the value of the vn compressed game, and by the compression theorem, this v hot at the index of 2 to the n is of value 1 because t is less than 2 to the n, and by the definition the verifier accepts, so that's equals to 1, and then the compression theorem says that this value is also 1. So by similar arguments, you can prove that no matter what t is, as long as it's some fixed integer, you can prove that this value is 1, and you can prove that when m does not halt, then this value is at most half, and that's for that we need to use the entanglement argument. Like the game is using larger amount of entanglement, and for the game to achieve value of half, there's no fixed bound of entanglement, and that's another way to say that the value of the entangled value of this game is at most half. Okay, we can also show explicit separation between these two values, and we do this by defining a different Turing machine where we first compute the game, and then we run NPA hierarchy to test whether it stops. The NPA hierarchy would detect whether the game has value, the commuting value less than 1. If it's less than 1, it will hot and tell you that it's less than 1. But like in our case, if NPA hierarchy halts, we accept. And if it doesn't halt yet, then we do the compression, and it's very similar to the previous definition. So our claim is that now the entangled value is at most half, and the commuting value is 1. So the proof of that the entangled value is at most half is very similar to the previous proof. You just argue the entanglement that is being using. But like to see that the value has to be 1 for the commuting operator value, assume that the value is starting like is less than 1. Then we know that the NPA hierarchy would detect this, and then from that you would see that entangled value would be 1, but like we know that the commuting value is always larger than the entangled value, and therefore it's a contradiction. So it cannot be that this value is less than 1, it has to be 1. So that's all the power that we get from this compress algorithm. So to summarize, we have been constructing recursive gap-preserving compression of normal form two-polar one-run protocols. It's for a very special family of protocols. And using this compression lemma and Kleen's recursion theorem, we are able to prove that RE, the halting problem, has a MIP star protocol, and therefore RE is in MIP star. And as we already know that MIP star is in RE, so the equality follows. And this, of course, gives negative answer to Tillerson's problem and Kahn's embedding problem. So there are some open problems. One is, can we have simpler proofs? Well, the paper has 160 pages, but I think that the idea is very modularized, that once you have all these ingredients, it's a very modularized proof. Another question is, there's another class related to MIP star called MIP co, where you're defining the values in terms of the commuting operator strategies. And we conjecture that this class is actually co-RE. Note that these two codes are of different meanings. And also, it's interesting maybe to come up with explicit counterexamples to the Kahn's embedding problem. While others is like where a sequence of implication known in the literature. Okay, so to summarize, it's very interesting to look at our results from the historic perspective that in physics, in computer science, in mathematics, and a lot of exciting results starting from the 30s and revisited in the 60s, 70s, and to the 90s, all related to this results. And basically by using computer science and quantum information techniques and resolving problems in physics and in mathematics. Thank you much for your attention. And so I guess it's a very condensed talk, a lot of concepts being mentioned. But I guess it's a good opportunity because we have 3 talks. I guess you have got a flavor of how the proof works, and this thing looks like a map, and hope that will help you to find your way if you really want to understand the proof. Okay, thank you.
Thank you for the talk. I think we have time for a few questions if someone wants to ask something. It's the right time. It's in Q&A if you are an attendee, or you can just unmute yourself if you're a panelist. So we have a question in the chat. Oh, sorry, it was not a question, just a virtual clapping. All right, so I wanted to ask when you apply the PCP theorem, then usually the PCP theorem is applied to like a particular like circuit. Yes. But here, like you apply the PCP in a way that it also depends on this unknown long string that the player samples themselves. So how do you check the content of that string somehow, because it needs to be included in the PCP proof in some way?
Yeah, that's a good question. So I think like let me try to bring up the what is it? So remember we have like 4 steps, and so the PCP is after the oracleization. Right? We have a game where the question sizes are small and answer sizes are big. That's your starting point. And what this PCP is checking is, because after the oracleization, the oracleized player knows all this question X and Y and A and B for this game, like for this game before the oracleization. So the oracleized player can compute a PCP proving that the verifier would have accepted this question and answer tuple because it's the oracleized player knows everything. That's most of the the checking is happening in this PCP part. But of course, we want also make sure that the Bob's answer and the localized player's answer are consistent. And it's not that obvious that you can do this, because once you encode this using the PCP, you may not be able to extract out the part of the information. And that's some extra condition, extra modification that we have to implement in this PCP step. So basically, we would make sure that you can easily extract the information from the oracleized verifier to check across with Bob. But the main part of the PCP is checking whether the decider will accept, like there's a decider in this step, and we want to make sure that this decider would accept in that oracleized game. So it's a decider. You don't like the idea is that it's like you don't need to send me the proof. You just need to send me the PCP proof that convinced me that I would have accepted if you send me all the proof. But the oracleized player know all the information, and that's a crucial thing, because previously when we use this error correcting code, then there's none of the players can do this, because they only know random information, and so that's really hard to work with. But now with EPRs, we have an oracleized prover who knows everything, and that's where this allows you to apply this PCP technique in the proof.
Okay, if there are no more questions, then let's thank again all the speakers of today, Alex, William, Joan, and Zhengfeng. And yeah, thank you for your great talks.